is my pleasure to introduce the speaker for today's colloquium, Professor Luisa Whittaker-Brooks. She is an associate professor of chemistry at the University of Utah. Her research is in the design of well-defined hybrid materials with controlled morphology and interfaces that serve as conduits for deterministic and coherent energy and charge transfer applications in energy conversion, energy storage, and electronics. So basically, she's a physicist in the chemistry department. She received her BS degree in analytical chemistry from the University of Panama. Then she had a Fulbright fellowship and received her MS and PhD degrees in materials chemistry from the State University of New York at Buffalo. She went to the Princeton University Department of Chemical and Biological Engineering to do a postdoc at Princeton University. And in 2013 was the recipient of the L'Oreal Fellowship for Women in Science Award. In 2015, the Marion Milligan Mason Award for Women in the Chemical Sciences. This is given by the American Association for the Advancement of Science. She was named a Cialog and Cottrell Fellow by the Research Corporation for Science Advancement. A talented 12 by CNN News, that's the Physics Today for Chemists. And Gera Ovinsky Energy Fellow by the APS, American Physical Society. She has also received the Department of Energy Early Career Award and a Sloan Fellowship in Chemistry at the Camille Dreyfus Teacher Scholars Award. And the floor is yours. Thank you, Lisa.
All right, thank you for the introduction. And thank you for inviting me here. All right, so let me start giving you a little bit of an overview. And something that I have to say is that, can you guys hear me in the back? Or do I need to amplify my voice? Yeah? Okay, let's use this. Yeah, so something that probably they always tell professors when they're starting is to focus their research program. The problem is that that doesn't work that well when you are interested in too many things. So my research, how close do I need to put this in my mouth? How close do I need to show it to my time? All right. Is that better? For me, it just sounds the same. Whatever. I'm just gonna hold the mic, I guess. Yeah. Then I can just like drop it. Okay, back is hot. All right. So the thing is that they always tell you that you want to focus your research program. But my research program is actually pretty broad, right? And that comes from the fact that I did my PhD in inorganic chemistry and then my postdoc in organic chemistry. So I actually switched fields, okay? And the thing is that whenever we think about what is happening here in terms of electronic structures, if we are thinking about organic semiconductors, normally we talk about molecules, right? So whenever we are assigning electronic structures, we'll say, well, I have an electron that's being excited from the highest occupied molecular, this is a molecule, orbital, into the lowest unoccupied molecular orbital, okay? The problem now is that we tend to form very stable electron hole pairs in that material, and we call that an exciton, okay? Then the thing is that the outer side of my heart is divided too, because then there is the inorganic side, right? Where we actually talk about free carriers, because now what we have is that an electron is completely excited into the conduction band, and they just get divorced. They don't like each other, okay? All right, so in this case, then my group is interested in seeing how we can bring these two worlds that are very far away from each other and then bring them to like a medium stage where they start liking each other, okay? And it also helps when I'm trying to, I don't know, find people to write me letters for awards and things like that. Okay, So the thing is that then we started working on these hybrid perovskites that basically have the organic and the inorganic component in there. Then my group started making these magnetic magnets. So we actually call them molecular magnets because we have the organic component in there. And then we started working with coding different structures with organic molecules or changing different heterostructures to make multi-layered systems, okay? The thing now is that we will say, well, we know both parents, right? The organic and the inorganic material. So according to genetics, it should be 50-50, right, on the traits. So you will say, well, in terms of charge transport, they will have some, I don't know, some variable range hopping where the charges would just hop between different molecules, or would take advantage of pi interactions, right? Or since we have a band-like transport, they're just free to move wherever they want to move. Okay? The thing is that these materials actually have their own identity. So in terms of like talking about biology, they just break out the biological rules, right? So they will be like what we will consider like they're breaking the second law of thermodynamics, right? Because they just follow their own thing. So that means that whenever we think about charge transport, they can actually follow all these different types of phenomena. So they can actually be band-like or have variable range happen or some sort of like defects mediated charge transport, or some percolation where you're thinking about films and whatnot, okay? So this is actually what keeps me awake at night, okay? Trying to figure out what is the charge transfer processes in these materials. All right, so the thing is I cannot present all of this in an hour without Mario yelling at me. He told me specifically not to go over an hour. All right, so what I'm just gonna do here is just slice probably 20% of the research efforts in my group that's actually related to metal halide perovskites, and then trying to understand how dimensionality affects electronic properties and device performance. Okay, and another thing that you will see that I'm going to be talking a lot about today is excitons here. And the thing with excitons is that as we reduce dimensionality, then the binding energy for excitons actually increase, okay? So as we move down this trend, this material is really good for photovoltaics, specifically solar cells. But then as we move to this material right here, it's not that good for for photovoltaics. But something that I always tell my students is there's a word that I just don't allow any of my students to tell me. And that word is, well, it's not a word, it's a phrase. It didn't work. And why is that, right? So it didn't work for me means that your dog ate it. I don't know, you flush it through the toilet, something crazy, right? And why do I say that? Because if you're thinking of using this as solar cells, normally you want to split charges, okay? And so it means that you want your binding energy for your excitons to be low so they can be split into free carriers, okay? So if the efficiency is low, it means that your holes and electrons like each other a lot. So they are recombining a lot. So if you have a lot of recombination processes, that is the opposite of a photovoltaic, which is a light emitting diode, okay? So normally when a student tells me that their solar cells didn't work, I'm like, well, can you actually make a LED, okay? So take advantage of that recombination process, okay? All right. Okay, so let's start with 3D. So with the 3D, basically what we have is this tetragonal structure, or in this particular case, yeah, it's a tetragonal structure, right? where I have a metal halide, so it's the lead iodide, and it's surrounded by organic component, okay? And this material actually caught a lot of attention because of their power conversion efficiency. So based on this very complicated embryo chart that I'm not showing you as a function of time, silicon mostly dominated this market, but I wanted to put information here, so I'm deleting it, right? So we are just focusing on what happened here in 220. So we have perovskites here at about 25.2% as the efficiency, right? Compared to silicon, which is at 27.4, okay? So in terms of efficiency, it's very close to silicon, okay? But it took us about 40 years to make silicon that efficient compared to perovskite, which took us from since 2013. So about 10, almost 10 years, okay? So the thing now with these materials is their device reproducibility and stability. So if you actually look at them too hard, they will degrade in front of you, okay? So, and this is actually a very good representation of what is happening here. This Petri dish right here is samples that we have fabricated because we actually go to the synchrotron quite a bit. So we end up making a lot of triplicates of the same material over and over and over, right? So all those films nominally are the same composition, yet they are degrading at different rates, right? So there has to be something that is triggering that decomposition in some films that is not triggering in the same film, yet they're the same composition, okay? So we thought that this has to be something related to grain boundaries that are crystallized or are forming different in these films, depending on the fabrication process, okay? All right, so we said, well, we know that, so is there a way for us to guide what is happening at the grain boundaries, okay? And how can we understand what is happening at the grain boundaries? So the way that we thought about that is just using a chemistry approach and said, well, can we actually glue these grain boundaries with these self-assembled alkyl ammonium cations? So we basically have these molecules right here. We add it to our solution, and then we spin coat our material, and then see how it affects the kinetics of the crystallization process to change the formation of crystals. And in that regard, the grain boundaries of these materials. Okay, so we did a morphological characterization here. So here I have my SEM micrographs, right? And what I'm showing you here is the size of the average size of crystal grains, depending on the system that we are putting in. So the first one is pristine, so it's just a control. So the grain sizes on average are about 490 nanometers. Then when we put the ethyl, grains sizes become bigger. So we got 520, ethyl increases to 860, so we have larger grains. And then the butyl decreases because it slows down the crystallization. I'm sorry, not slows down the crystallization. It increases the crystallization, so things start to crystallize faster. So the grains are actually smaller. Okay, so then we said, well, can we actually look at what is happening in terms of 2D maps to understand what is happening at the surface and the bulk of my material? So we actually did another technique that is called GI wax. So Grayson incidence wide angle X-ray scattering. So in the QZ, we are looking at information out of plane of the film. Then in the QXY, we are looking at information in the plane of the film. All right, so then what we can do, we know that this is the signal of some crystallographic plane that in this particular case is what we call the 110 plane. So if we asymptotically integrate all the intensities around that, then we can say which one is more crystalline, okay? So the brighter where you just look at it and then you want to play, which one is more brighter, then you can probably play that game, but I don't think it will get published if we actually do that. So we do that, we asymptotically integrate, and then we see that whenever we put the self-alkyl ammonium cations, we gain an intensity, which is an indication that the crystallinity is increasing when we put in these alkyl ammonium cations in there. All right, so how about optical properties? Because we don't want those to change as a function of us tuning or mucking around with the morphology, okay? So we know that there's not a change in the absorption. They have basically the same band gap. The PL signal is basically the same. So we know that we are not changing the optical properties by changing the morphology. All right, so before actually making devices, there was a professor that retired, and then he's like, "Oh, do you want this setup?" Yeah.
You're saying that changing the morphology is not actually changing the optical properties.
No.
So when changing the morphology, actually changing the radius of the grains, it should affect the scattering property of the, like I said, the smaller the radius, it should scatter more. So we should see the change of optical properties, changing the material size.
Right, so that would be correct if you actually had a two-dimensional system, right? But in a three-dimensional system, you basically cancel everything out in all dimensions. So you wouldn't see that change in a three-dimensional system. But in a 2D or a 1D, you will see it because of quantum confinement effects. Yeah, that's correct, but not for 3D. But that's good. Okay, so the thing is that then this professor's like, all right, take this setup. I'm like, whatever, then put it in my lab. So we started assembling this. So we ended up doing these transient absorption, transient reflection experiments, right? So with transient absorption, we are basically probing the bulk of the material in order to understand how defects are formed, or the amount of defects that we have in these systems, right? So you will see that there are two signals here. So one that is positive and another one that is negative, right? So the thing is that one is basically the ground state photobleaching, so the positive one, and then we have the negative one that is basically excited state absorption. All right? Okay, so that is just the signal right there. Then we translate that into a lifetime, okay? And what we see here is that there's an increase in the lifetime when we put the alkyl ammonium cations in there, okay? And that is an indication that we are passivating grain boundaries within the bulk of the material, okay? So then we change the arrangement of our setup to do transient reflection. So now with transient reflection, what I'm doing is just looking at the surface, right? And again, if we focus on the lifetime, then you will notice that there is a faster lifetime for the reflection data, right? So whatever is happening in these materials at the surface is faster than whatever is happening in the bulk, okay? So this is, again, an indication that my surface has way more defects than what the bulk has, okay? But then at the same time, we see that there is an increase in the lifetime here, which again is an indication that we have higher density of defects at the surface, but we are passivating those with the alkyl ammonium cations as well. Okay? So, all right. My student wanted to start making cells. I'm like, sure, start making these cells, right? And then there's where hell start happening. Well, finally, I'm not supposed to say hell. Oh, I'm not in Utah. It's okay. I totally forgot about that, but whatever. Okay, so the thing is, with perovskites, every other week they start changing the composition because certain composition give you the highest efficiency. Okay, so we started playing with these compositions, and I'm like, this is just nonsense. So we actually stayed with two different compositions here. Okay, so the mixed halide, where we have the iodide and the chloride, and then the triple cation that basically have every other cation that you can find under the sun. So yeah, I basically call that the soup. Okay. So the thing is that this triple cation actually give you the 25.2% efficiency that you see. That is the record. Okay. Over this one that gives you 20%. But that difference actually determines where your paper gets accepted into. Right? Which is stupid. Anyways, all right, so we started making cells with these two, right? So we actually did time resolved photoluminescence to look at carrier lifetimes. So we know that we have an increase in the carrier lifetime when we go to the 3% propyl ammonium iodide, right? So it means that there's less chances of, the recombination paths for these materials is lower, okay? So then if we actually look at the IV curve, right? So here I have my short circuit current. So the current that I'm generating at voltage equals 0. Then here I have my VOC, so open circuit voltage. So the voltage that I'm generating at current equals 0. And then we have the squareness of this data, which we actually call the fill factor, and is the affinity of all the interfaces, how much all those interfaces like each other. So the more square it is, it means that they really match each other very well, okay? So that typically, you will never get anything higher than 80% of likeness, okay? So it's like a marriage. So you will never get a marriage that is 100% likeness. So the fill factor, the theoretical fit factor of a marriage is 80%. So it's the same thing with solar cells. So what you do, and you end up multiplying these three things, and then you get your power conversion efficiency. So the amount of solar energy that you convert into electricity, okay? So again, we are something around 20% versus 25% for the highest. And then for the propyl ammonium, we are at 19.46. I already told you that these materials degrade very quickly, right? So we actually have to look at the recombination. So we know that there is a decrease in recombination when we use propyl ammonium iodide. And now stability in air and humidity conditions, okay? So we actually did look at the power conversion efficiency as a function of storage time in air, under light conditions. So this is under illumination. So 1,000 hours of a lamp is a lot of lamps, okay? So the thing for each solar cell, so it was actually a lot of lamps. So this is 10 to 15% relative humidity, which is about the relative humidity in Utah. Yeah.
What are those groups for?
The what?
What you call this initial rate?
Oh, yeah, because that is the moment where the cell actually equilibrates, right? So the thing is that if you're starting here, whenever you turn on the lamp, you are not at you're not at what we call 1.5 AMG. So the light intensity is lower here than what it will be here. because the lamp is not hot enough. That is the right word that I want to use. So basically at this point 0, the lamp is still off, right? And then I start the experiment and then it has to turn on. So yeah, if I wanted to take this out, I will have just turn on the lamp, wait until the lamp equilibrates, and then put the solar cell in there. But just do it from the scratch. Yeah, that's basically what it is. Okay, so 10-15% relative humidity is fine in Utah. 45 to 50, we actually have to artificially make that because it doesn't get that humid, right? But then what we see is that with the propylene ammonium, we don't lose in stability that much. Okay, so the thing is that this field, and that is a big concern, is very obsessed with trying to figure out ways of getting rid of the instabilities in perovskites when it comes to environmental factors. Okay, so the thing is that we actually wanted to know what happened with voltage and current instability. So device instability over environmental factors. Okay, and yeah, I can probably spill the beans and say that we actually move away this because too many people were trying to understand that. So we wanted to understand what would happen if I apply a voltage or current to these systems and how things will change. So what do I mean by that? So if I have a voltage, if I'm applying a voltage as a function of time, right? And then I see what is happening to the current. If there's no stress, then the current will not change, okay? But then if there is a bias effect or a bias stress, then you will see that the current will start going down, okay? And then it will keep going down until I release that stress. So whenever we release the stress, it will go back up to its original position, or it will partially recover. Okay, so we actually want to understand what will happen there. So we designed this experiment where we actually do pulse voltage stress effects, voltage stress effects. So here, basically have an IV curve, since I'm not using the laser, might as well. I have the IV curve here, and then we pulse at different voltages and see how the current changes. So you will notice that at higher voltage, there's this huge V shape going on here. So it's generated more current, okay? The problem now is that this is actually acting as a capacitive effect. So instead of making a photovoltaic, we're actually making a capacitor, okay? And why is that dangerous? Because whenever you are reporting solar cell efficiencies, people normally don't take into consideration that, okay? So it means that your efficiency is gonna be inflated by whatever that change is. So for example, this is actually giving us a power conversion efficiency inflation of 30%, okay? And that's why there's so much device reproducibility from group to group in terms of getting the right efficiency, okay? All right, so then we said, well, how about what happens with the change in current, okay? So these are post voltage measurements. So we look at what the current is doing. So for the mixed halide, we pulse the voltage. So we apply a voltage, right? And then hold that voltage and then see what's happening with the current. And then it give it some time, and then we turn it off, and then let it rest, and then we turn it back on and do this multiple times. All right, So for the mixed halide, so the one that has iodide chloride, we see that there are these spikes that are showing up here regardless of the voltage. And then for the triple cation, we don't have any spikes, okay? All right, so we are scientists, and that is a problem, that we never stay at just saying, well, there you go. One has spikes, the other one doesn't have spikes. Let's leave it there. What is the next step? What is the next step? Why, right? We, as I said, we are scientists, and that's why we complicate our lives. Just asking why all the time. Okay, so why are these spikes in there, right? And the thing is that normally you go and you design an experiment to understand the whys. And I basically use my background in organic electronics. And in organic electronics, we always blame everything on morphology. And that is exactly what I did here. I blame it on morphology, okay? So again, we're doing grazing incidence wide angle X-ray scattering experiments. Then for the mixed halide, we will notice that there's a lot of brightness in the QZ and a lot of brightness close to the QXY. And then there is mostly brightness here in the triple cation at what we call the 45 degree angle. All right, so, oops, oh geez, I went all the way, yeah, you see, I got it between an hour. There you go. All right, where am I? Oh shoot, I even know the numbers, almost. All right, so the thing is that then, again, we can asymptotically integrate this, so we get most of the intensity here for the mixed halide, triple cation over here. So in terms of orientation of the film with respect to the substrate, and this is important in the next slide, right? We know that the mixed halide, the 110 is oriented in this direction. And then for the triple cation is oriented in this direction. Okay? All right, so why is that important? So then we just did, we are not theoreticians, but we actually like to use models very well. So we actually went and we calculated the activation energy of these materials in terms of ion motion. So we know that the activation energy for iodide, that's metal halides are ionic materials where you will see a lot of ions moving. So the iodide has an activation energy that's pretty low, so about 0.3 eV. The methyl ammonium cation is higher. Lead is about 2.2 eV. So we actually don't talk about lead migration. That's just too heavy, okay? And that actually correlates with the diffusion coefficient. So the iodide has a higher diffusion coefficient. Okay, so we know that iodides are going to be moving over the organic cation. And then we can also look at what planes will favor this ion migration pathway, okay? All right, so here's just the representation of the crystal structure along the 110 plane. So we know that the halides and the lead will move along the 110, okay? And the cation, in this case, the organic cation, so the methyl ammonium, will move along the 100, okay? So this cartoon here is not drawn to scale. It will just look weird if we draw it to scale. The thing is that these purple balls, and I actually learned my lesson by making purple balls instead of blue balls because they used to be. So these purple balls right here, they should be closer to each other, okay? And what will happen is that this 110 is not due to sterics. You will not have that methyl ammonium traveling in that direction. So if it really had to go and go into this vacancy, it will have to hop, okay? So again, that probably is very unlikely. All right, so going back to what we see in terms of morphology, right? So we know that the mixed halide, the 110, is oriented in this direction. And I'm making photovoltaic devices. So these are out of plane stacks. Okay, so we normally call them diode-like stacks. So I have my electrode here. Okay, that is supposed to be collecting all these charges. Okay, but then I have my 110 in that direction where my halide, so my ions, are also moving. So what will happen is that whenever I shine light, then I'm going to have accumulation of ions at this electrode interface. Okay, then if we go for the triple cation now, again, I have my electrode up here, but it doesn't have the right configuration for my ions to migrate towards the electrode. Okay, so that's why we will see that based on morphology, my ions will transport very well in this mixed halide, right? Whereas ions do not transport very well in the triple cation. Okay, and I'm actually making better choices of words here by saying better and not that well, because for photovoltaics we actually don't want those ions to be get into our electrode. But if you're actually thinking about applications beyond photovoltaics, right, like resistors and things like that, you actually want those ions. Okay, so in terms of that, this system is better for the resistors. This system is better for photovoltaics. Okay, all right. So let's go into 2D-ish. So now what we end up doing here is that the 3D system, you can basically think about using a scissors, and that scissor is basically like a big organic molecule, right? That is just cutting the 3D system into two, okay? And then by doing that, then you end up making that two-dimensional system, which arguably is not really a two-dimensional system because you have the organic system in there, and it's not really held by van der Waals forces, right? So it's not like your typical two-dimensional system that you would normally think about, right? But the thing is that we normally, the definition is coming from the inorganic community that don't care about organic molecules. So for them, the organic molecule is not in there. So that's why it looks like a layer system if you just, block all the organic systems. All right, so what is the thing? So we move from 3D to 2D, and what ends up happening is that now you have your metal halide and your organic molecule, so you will have a low band gap material here, and then a high band gap material in there that would actually give you a lot of confinement, okay? So then in terms of dielectric constants, right? So you have a low dielectric constant for the organic material and a high dielectric constant for your inorganic material. So again, you have a lot of dielectric confinement effects. All right, so whenever you have that perfect storm going on of two mismatched materials that really want to be together, forming these quantum wells, okay? Then, so basically you have these wells in here where now you have your electrons and holes that are confined within the wells. And again, the best thing that they have going on for each other is to recombine. So they form these very stable excitons, where the exciton binding energy is about 100 milli-electron volts. Okay, so they have isotropic carrier mobilities. Frankel type carriers is basically driven by excitonic properties, so that's basically what Frankel type carrier means. Then you have a heterogeneous dielectric medium because of the dielectric mismatch between the two layers, okay? Compared to bulk silicon, for example, right? Where now you just have electrons that are excited. So you have mainly free carriers because the exciton binding energy is very close to thermal energy, right? So then carrier mobility is anisotropic. You have Warner type carriers, basically free carriers. And then it's a homogeneous dielectric medium, okay? All right, so the thing is that quantum wells is not something new, okay? And it actually came from gallium arsenide, okay? So this was actually, there's a history for that. So in 1960, we started making, ways of growing these gallium arsenide structures by molecular beam epictasy, right? Then in the 70s, we started alternating layers of different, high band gap and low band gap structures of gallium arsenide. So basically aluminum gallium arsenide, heterostructures that created these quantum wells. Then we started understanding the excited state properties in these materials. So we, in the 80s, just gave me a deja vu of when I was born. We started measuring, modeling things. And then in the 90s, we started putting these things into devices, mostly like light emitting diodes and things. So we knew how to tune. And then 2000 came in, and everybody just forgot everything because graphene dominated physics, right? And nobody wanted to hear anything else. And everybody just forgot everything else. Okay, so I am an anti-graphene person. So I always try to do everything that is far away of graphene as possible because I hate that freaking Scotch tape thing. Anyways, so the thing is that we wanted to use some of the information from the gallium arsenide community to measure, model, and tune in perovskite materials. Okay, and why is that? Because some of the excitonic properties of these materials are responsible for the light absorption, emission, or charge transport, but it ultimately affects the bottom part of that pyramid that I have at the end that relates to what kind of device architecture I'm going to use, what electrode material device I'm going to use, what quantum device I'm going to make, okay? All right, so we decided to say, well, can we actually understand what is happening in terms of measuring the excitonic properties of metal halide perovskite with respect to gallium arsenide? The information is there. Probably have to go to the library because Google will not have it, but it's there. We actually have to go to the library. So what is the problem? Okay, so for example, I'm showing you here this structure. So it's butyl ammonium lead iodide, and probably is the most studied 2D metal halide structure to date. And then if you actually think about the values out there for the exciton binding energy, it varies quite a lot for this same material. So it's the same system. It goes from 160 to 490 milli-electron volts. Okay. Then this is the variation that people have shown in the literature. There's only one paper talking about the exciton radius. Compared to gallium arsenide, aluminum gallium arsenide, the statistical variation in the experiment is way much tighter, okay? So there's not a lot of deviation there. So we're like, all right, so what are they doing that we are not doing right, okay? And what they're doing is actually using a technique that we have to like resuscitate in our lab that is called electroabsorption. And basically what we're doing is just applying an electric field and then seeing how the absorption is changing, okay? Then you just take those two, and then you get the change in the absorption under field and under the with no field and with field, and then you will get this signal right here, where at lower wavelengths you have information that comes from localized states, it's mostly excitons, and then your delocalized states, that is information related to anything that is close to the band gap. Okay, so if you have any defects that are bleeding into the band gap, you will get that sort of information. So the way that we have to do this experiment, because we are now applying an electric field, okay? And if we are applying an electric field, right, and it's pretty high, so it's actually 100 volts. And I'm like, all right, so this is high, but it's actually AC. So it's not that big of a deal, it's still high. But the thing is that if you actually make like a diode-like structure, so out-of-plane structure, the film disappears in front of you because of the high field. So we actually had to change the arrangement of the film to actually have an interdigitated electrode to minimize Joule heating. Okay? So then when we actually end up making that sort of substrate, then we actually, while we were making the substrate, we were digging the literature. So we kind of went all the way back before I was even born to find some papers here on, I'm narrowing down on my birthday. So on these papers here that actually give us a lot of the models that we can use to look at the electroabsorption response in these perovskite structures, okay? Compared to the quantum wells, so you'll notice that there's a lot of papers here that have a lot of citations and people using them to model exotonic properties in quantum wells. There's not a lot of papers in perovskites, and there's a lot of electroabsorption studies. There's a few, they're contradictory. So basically, group in Japan and I going back and forth on our arguments. And that is because of, and the irreproducibility is coming from lattice effects, right? And why is there, where is that lattice effects coming from? So from here, so we all agree that this is peak related to excitons. But now the difference that you have from this peak to whatever is happening over here will determine what your binding energy is. So if you don't know where to set that, then you will just have that variation in your exciton binding energy, okay? So now the problem is here, like what is this peak, okay? And well, what is this one too, right? All right, so that is what we actually wanted to understand. So what we end up doing is that we collected a lot of electroabsorption on many compositions of metal halides. We put in lattice effects and we simulated the electroabsorption spectrum by solving some equations here. So let's look at the model. So the model is very simple, right? So we can treat it as a hydrogen model, right? So you basically have a hole and an electron. That's it, right? So the thing now is that since you have that, then you will have some sort of Coulombic interaction going on, right? They are moving. So then here's where your kinetic energy term comes into place. And then you're applying an electric field, okay? So there's those three things that we have to take into consideration. The problem is that it doesn't have a direct solving of that Schrodinger equation, right? So we basically have to go through our numerical procedure to find what the right fit of the electron, or what the right model of the electroabsorption spectrum is. The problem with that is that, again, we have to rely a little bit on the literature because now the electric field is related to the effective mass. So we have to use the effective mass that is in the literature. And then the dielectric, as the same as the dielectric constant. And then we have this homogeneous broadening, which is from the absorption features that we are getting from our signal, okay? All right, so the first iteration of the model gave us this simulation right here. This is actually the measurement, and then we can actually find the differences, I guess, right? So then you will notice that there's something missing here that is actually here, right? And that is actually related to the fact that we are not contemplating lattice effects in the simulations, okay? Which we actually had to put in eventually, and then you will see that right there. But then we actually learned that this is related to the band edge, and I'm gonna show you why in a second, okay? So now that we know that, then the difference between the excitonic peak and the band edge will give me the exciton binding energy plus minus 3 milli-electron volts, okay? So it's a very tight fit. Okay, so then from the binding energy, then we can get all these different measurements of the effective mass, the pole radius, polarity stability, dipole, things like that. Okay, so we know that this is actually related to the band edge because it's field dependent, okay? And if we actually fit this to the field to the two-third, we get a straight line. If you actually fit any other peak to the two-third, then yeah, it doesn't fit that well, okay? So that is an indication that we actually have a band edge feature. Well, on the other end, then if we actually don't fit it to the two-third, but then we have the applied field, then we can get all the rest of the information here, right? And then we will notice that even though that we are modeling a 2D exciton, these materials really don't fit 2D, and we are using gallium arsenide models, right? So it doesn't follow really the 2D excitonic features that you will see in gallium arsenide or 3D exciton. So it's something in between that we have to eventually figure out. Okay, so we know how to measure. We know how to, now we want to know if we can actually find ways to manipulate things. So the nice thing about perovskites is that it saves us about $1 million because we don't have to worry about molecular beam efficacy, as we just need like a $10,000 spin coater, okay? So that's nice, right? And it gives you a lot of information, a lot of opportunity to vary composition. So for the iodide, we actually do electroabsorption, and we have this right here. Then the binding energy is about 222 milli-electron volts. If you go to bromide, it increases to 349. Okay, what is my computer doing? The chloride, which is 487. Okay, so we did this for 21 other structures where we are varying the organic and the inorganic component. So we know that we have tunability according to the organic layer in one direction, and then tunability in this direction. But still, the fit, like the variation that we're seeing is pretty broad because not all of them are following the line. Okay, and that is actually related to lattice effects. And the way that that is related to lattice effects is through the dielectric constant, because we're not computing the right dielectric constant. We just took the one random dielectric constant that we found in the literature. So we decided to model our dielectric constant based on, again, gallium arsenide. And what we need here is the dielectric constant. So we designed an experiment where we did capacitance measurements, again, using our substrate, right? Then you will get, your change in dielectric response as a function of frequency. Lower frequencies will give you information on ion migration. Then from the higher frequencies, you will get information related to phonon and electron interactions, right? And we complemented that with some very basic DFT calculations. Okay, so we designed the experiment. We just did some standards here. So this is squares. We're not going to see that much of a difference. But then this is getting the dielectric constant of water. And these are different waters, right, with different ions in there. And then that's why you see that this is different. Okay. So then on the other end, we have our perovskite film. So this is 3D, right? Then this is 2D that has a lower dielectric constant, which for the DFT is given of 6.18. So that is bulk dielectric constant, right? So we want the dielectric constant for each of the different layers, right? So we actually use this formula right here to get what the dielectric constant is for the organic component and the inorganic component. And then when we did that, then we added to the binding energy that we were getting in there as a function of band gap, then you will notice that there is, all of them follow the line, okay? So now the issue is that we had to use the same dielectric constant for all the different compounds. So we actually had to measure the dielectric constant for each of the compounds that we were doing in our study, okay? All right, so then with that, then we look at the how the organic barrier changes the exciton binding energy. So when we increase the organic length, we kind of plateau because they don't feel each other that much. So there's a lot of screening of the exciton, right? So the binding energy doesn't change that much. Then when we change the inorganic layer, then again, as you increase the number of inorganic structures, it resembles more of the 3D. So the exciton binding energy decreases towards free carriers, okay? And then most of this experiment was actually done by physicists, actually, right? So we had two issues going on. The films actually are heterogeneous. So I gave them two options. I told them, can you just go to the lab and make films that are pure, or can you find a way of quantifying the different heterogeneities that you have within the film? If I would have asked that question to one of my chemistry students, I think they would have gone to the lab and done wet chemistry. But no, he decided to go to his computer and mess up with MATLAB codes in order to make ways of understanding heterogeneities in the film over going to the lab and making a pure film, whatever. So he ended up doing these electroabsorption fits, right? Where you have different phases within the film, and then he fit the data, right? We had to take into consideration something that we call oscillator strength, right? And then relate that to binding energy. So if we know the oscillator strength, then if we know the binding energy, then we can correlate what the oscillator strength is. We know the binding energy for single crystals. So then based on his fit, then he determined this percent composition right here, which actually tells me the amount of phases that we have within the film. So this is actually done at 15K. So for the n equals 1, there's a phase transition, so there's a memory effect. So at 15K, we actually have some of the room temperature phase still at 15K, okay? So that's what you're seeing for n equals 1. For 2, 3, and 4, we just have different structures in there, and we know what is the amount for that. Okay, so let me quickly talk about 1D. So that's gonna take you like 1 minute, promise, right? So the things that I said my heart is divided in two, so I actually have an organic cap as well, right? And the thing with organic materials that they suck, okay? And it's actually nice not to be in Utah because I can say suck too, right? So the thing is that we try to find ways of creating dopants that will increase the carrier of these materials, okay? So we end up putting out these dopants in here, and then you have these, an increase in the spin concentration of these materials because you end up forming radicals, and these are half spin integers, so you can actually map them by doing EPR. Okay, so the thing is that we wanted to do this, and we recently got this published into Advanced Materials, and wanted to know if we could actually take these molecules and combine it with perovskites, right, to actually make organic inorganic scaffolds based on these structures. All right, so we ended up making these single crystals, not with the beryllium diamide, but with the naphthalene diamides, right? So it's actually smaller. Okay, so we were aiming for a two-dimensional system, actually making one-dimensional systems where we make films, and then we see this very strong excitonic peak and this shoulder right here that is basically some charge transfer states. So we map that again by doing transient absorption experiments, looked at they are very long-lived carriers, right? And then we complemented that with some unresolved microwave conductivity, where you're actually looking at free carriers, okay? And I'm just gonna leave it there to see if anybody was paying attention to me at the beginning. But with free carry, with time-resolved microwave conductivity, you are measuring free carriers, okay? So you're not measuring excitons because you're exciting that and then looking at free carriers, okay? So with these one-dimensional systems, we have free carriers. And I'm just gonna leave it there to see if everybody's gonna ask me that question. So then the thing is that then we can say, well, what is happening is that we have an exciton that is traveling to an interface and then splitting into a hole and electron, and then that electron is being transferred to the organic component, okay? All right, and that is actually pretty exciting because now we know that we can reduce the exciton diffusion length in these materials compared to what you will see in organic electronics. So the exciton diffusion length in organic electronics is 10 nanometers over the exciton diffusion length in these materials that is at the atomistic level, okay? All right, so with that, I hope that I show you that, you know, by thinking about the dimensionality across different landscapes, we can take advantage of the change in the crystal structure to think about looking at different excitonic properties, multiple phase memory effects, traps in these materials, and how this is correlated to morphology and structural changes, and how these ultimately affect device performance and stability. So with that, I have to thank my group members. So so the ones in blue are the ones that did all the work, right? And then the funded agency is the one that is funding this project. So with that, thank you, and hopefully we get some questions.